Hello again. So I'm going to talk about things like incoherent sheets and their singular support. So this and and, also as a reference, I will recommend the same outline paper. This is the root section. All right, and let me start. So there were basically three things I want to talk about. I want to talk about the notion of singular support for coherent sheets. Then I want to talk about incoherent sheets, and then I want to see how the two things can be put together. So the first part will be about, yeah, right. And let me maybe just to summarize the whole point, I think, as Sam pointed out in his talk, and he's not here, so I can say whatever I want. So the whole point is to modify slightly the category of quasi-coherent sheets. So all of this, in some sense, is about fine-tuning the categories that we work with in a way that would make the statement at least possible. And as we will see later, that actually correct. Okay. So singular support, first of all, what is it? Well, singular support exists in many different situations, and it always refers to the to a kind of set invariant which measures not just vanishing of something, but also direction of vanishing or non-vanishing. So we refine the notion of support to indicate directions of non or vanishing or non-vanishing. So that's in general. Now, specifically, we'll look at coherent sheets. Coherent sheets.
Could you please clarify what do you mean by direction?
I mean, I don't have to answer that. This is all like split repetition. So I'm not trying to make this precise. Or rather, I'm trying to make this precise, and that will take this. So, but now I can be precise. So I want to define an invariant that takes as an input a coherent sheaf on a quasi-smooth scheme, and then later we'll apply this to stacks. I guess the moment I say quasi-smooth, I mean quasi-smooth derived scheme, or it can be, in a classical world, it can be a classical local complete intersection. And for us, the main example for the geometric Lehmann conjecture, the main example where we will apply such things would be and then apply to the stack of local systems. So that's where this is going. Okay, now what is somehow I was trained to put this word, use this word first, and it's very hard to break the habit. So I'm going to do this now. So yeah, so let me say a little bit about the geometric meaning of the real slope. So the easiest thing would be to say that quasi-smooth means that tangent complex. Let me use the cotangent complex is concentrated in degrees -1 and above. So if it's degree 0, that means something is smooth. So -1 means it's not smooth. You can have, so you have something like something smooth, then you have relations, but that's it. And so this means that locally, our this okay, I just realized that in my notes I used X for the scheme, which used to be a term before. Hopefully, let me try. So locally, X is going to be of the form. I mean, I can write it as point times smooth. Smooth. In other words, I have two smooth schemes, which for now I don't need a name for. Then there is a point in the target, and I'm taking the fiber of this map. So this is my max. And so if the fiber has expected dimension, then it's going to be classical, and that's local complete intersection case. If it doesn't have the same dimension, as in the case where we impose unnecessary conditions like 0 equals 0, then you have to consider it as a derived scheme. But other than once you accept this, there are no particular difficulties with this case. Okay, so we have this, and then F is going to be a coherent sheaf on X, where, as usual, when I say coherent sheaf, I really mean an object in the derived category. So if we're in the classical world, this would be what's called IndCoh. Okay, so this is the first thing we can learn about singular support is that it's something we assign to this kind of sheaf on this kind of object, on this kind of space. Okay.
What do you say degrees? You like Torah amplitude?
Sorry, Torah.
What do you say degrees for the potential complex? Is that?
I mean, if it's right, so if it's a scheme, then it's just 2 degrees. It's just 0 and negative.
Cotangent fibers.
Okay.
You want to say cotangent fibers.
Does it matter? I mean, okay, yeah. No, you're right. What I mean is that it sits in, of course, that it's equivalent. Good point. So cotangent complex is in degrees -1 and above, meaning that it's equivalent to a complex of vector bundles sitting in degrees -1. So it's like you're right. I should say Tor amplitude. -1. Hey. Did I mess up? Not yet. Okay. So, all right. So this is what goes. This is what goes in and what gets speed up. So, there we to such and so the big thing. Let's make it big. So to such an F maybe. So F sits in the. And to it we associate a set called the singular support of F. And this set is contained, it's a subset of something. I guess we can have many different. It sits in something that we sometimes denote by sing X, but what it is, really, it's like the shift or this part of the cotangent bundle sitting in degree -1, which you can define as spec of the symmetric algebra on basically, let me just write on H1 of the tangent. So, I mean, you can expand this definition, but let me work out this one. So, so suppose that let me even assume that all of this both of the smooth things are affine spaces. So I start with an affine space, A, and then X is cut out by by setting a bunch of equations equal to 0. So this map will be F1 through Fk. The point will be 0, 0, 0. And so X is the common zero locus of a set of equations. And again, if it has the expected dimension, that is to say n minus k, it's classical. Otherwise, you have to think about it in the derived.
So you don't mean x equals to a.
Yeah, maybe. Okay. So, right. And so in this case, I mean, we know how to, we have a computation of the classical computation of the cotangent space to X, or tangent space to X, if you like. Like if you want to find the tangent space to X, you have to look at the common zero locus of the differentials of these things. And somehow it turns out that this shifted, the shift will correspond to having dependencies between those equations. So that's general views. Now the precise calculation, I mean, let me not mix notations, let me just use thing. Let me just use thing X. So the thing X will look as follows. It's a bunch of points X, A. So X is an X, A is a K couple of points, where A is give you a relation between the differentials of those points. So it's df1 between the differentials of the function. So A1 blah 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 plus AK dfk x. So so what does this mean? I mean, first of all, let me try to draw a picture. So there is the affine space X, potentially singular, sits inside it, and then over each point of X, we're looking at various relations between the differentials of equation. So at the point where X is smooth, by definition, these are going to be linearly independent, and so the only possibility for AI is going to be 0. So over the smooth locus of X, we just have a copy of X. And then at a singular point, the rank of this system of linear equations will drop, so we will have more solutions. So over singular points, we'll suddenly have a vector space of higher dimension, but the dimension cannot get worse than K.
Okay, on the board, is it, there's a plus, should that be a couple, like the F1 of X plus?
Where there's only one, there's one equals, this whole thing equals 0. So that AI, so you have coefficients between differentials of, so like coefficients of a linear dependence between differentials of a function of this equation.
Pushing the board up with it. Not visible.
So I guess that actually not in an intentional way, but that rhymes with the discussion of the map from local systems to bundles. This is, I'm tempted to say that this is a vector bundle over X, and its fiber over every point is a vector space, but it's not, the rank is not constant, so it's this, it's that kind of object. Yes.
And why is it a plane and not a line over the point?
I mean, I don't know. I wanted to make it clear that it doesn't have to be, that it doesn't, I mean, depending on, yes, it could be a line, it could be a plane, it's like over a singular, yeah. Yeah, specifically for the, if it's just like, if X is given by a single equation, like this picture might seem to suggest, then because there is only one equation, k is 1, and so it will, and this is actually, this is classically a famous case, which, I mean, definitely goes back to Eisenbart, and there are, so where if you just have a single equation, then either a point is smooth or a point is singular. If it's smooth, so if it's smooth, you're going to have just 0 thin, and then if it's singular, you have something one-dimensional. And so it's almost like either support jumps at this point or it doesn't. Any other questions? Right, and so now let's go back to this general outline. So to a point in to a coherent sheaf, we associate a subset in this object. So let me maybe continue. So let's say I have something of this sort, and because over smooth points of X, there's no difference between this locus and X itself, we get no real refinement of the original notion of support. So basically either a point is present or a point is not present. But then over the points where you get something higher dimensional, the singular support can have some non-trivial behavior. And the reason I draw it like this is because it has certain properties. So which really, I mean, at least for application, they may even be more important than the definition. So let me summarize the properties and then we. So properties, first of all, this F itself has bounded Tor amplitude, or if we want this to be fancy, so F is perfect. If and only if the singular support is contained in the zero section. And so at smooth points, this condition is automatic. So at smooth points, sort of both sides of this equivalence are. And then at a singular point, you will get something like this exactly when your F cannot be locally written as a, does not have a local resolution of vector.
Sorry,
Mhm.
maybe naive question. What do you mean by zero section here? Oh, okay.
So AI equals 0.
Oh,
So there is a copy. So it's not really a vector bundle, but it still has a copy of X embedded into it. Okay. Right. So then it behaves in an expected way for cones. So if I have an exact triangle, then the singular support of an extensional line, however you want to think about it, will be contained in the union of the two others. And finally, it behaves in a reasonable way with respect to it's with respect to operations on X. I'm particularly so behavior with respect to maps. And there are several things you can say, but the one that's most important to us is that if when the map is smooth, or smooth F, so that's the most important one for us because, or the easiest one to formulate, because when the map is smooth, sort of the type of singularities upstairs will match the type of singularities downstairs. So in this case, when the map is smooth, I mean, let me just write one line here, even though it fits the corner, so that in this case, then sin y is going to look like the base change of single x, and so that's the situation when where it's reason, I mean, you kind of know what functionality to expect, and I claim that it actually holds. Okay. So I still haven't told you anything about what it is, but at least I told you what, some features with its behavior. Are there any questions at this point? Yes.
Is the formula still you're replacing by singular support?
Sorry, for this?
Yeah.
Well, I mean that if I have a sheaf on X and I pull it back to Y, then singular support will be obtained from the singular support on X by fullback. So that's the condition. I can give it. For smooth F, it's easiest to formulate. If F is singular, you're going to have to think of you can ask a bunch of questions. And there are certain things that are natural to expect. The claim is that, they hold. This is the simplest such natural thing.
Do you feel something for tensor product?
So, well, tensor product is a kind of a pullback because tensor product is box times and then with a pullback, but it's a pullback for a non-smooth morphism. So once you fix this statement, once you say what to actually expect for non-smooth morphism, then you get a statement for tensor. Okay, so let me actually give you the definition so that you can work out all these properties on your own. And the definition is, well, classical. I don't know, by the way, does everybody know what classical means? There's a particular meaning in mathematics. Right, so classical means something that was proved before I defended my PhD.
The classical definition, R is known to at least 5 people for at least 6 months.
That's but I think somehow I find that the PhD definition somehow, I don't know, psychologically correct. So, okay, so let me say how this singular support is defined. So basically, the main idea is that it's defined via cohomological operations. So definition of sketch of definition. So so the claim is that, for example, in this case, coordinates along the extra variables, along the variables ak, or in general, functions like linear functions, these generators of the algebra of functions on your on the singular support. So this, what I denoted by h1 of tx, maps to x2 from f to itself. So, and again, part of the exercise is to figure out how this map works. It can be done very classically, for instance, in this kind of setting. And so, and by the way, this is factorial enough, so in reality, I should be writing the Hochschild homology here. And so, because it maps to x2, we're going to get a map from the symmetric algebra to the algebra of x. And then there's a classical theorem by Gullikson that claims that the X algebra of F is going to be finitely generated over these cohomological operations. Is finitely generated as a C of H1 dx module. And then we are going to define the singular support to be the support of this module over this algebra. F equals the support of this. So, for example, I guess I wrote some of the properties of F, but some of the properties of singular support, but I didn't mention some geometric things except for this picture. So, from this, from the definition, you can see that because you have a graded module over a graded algebra and it's finitely generated, you know that the singular support is going to be Zariski closed and conical. This is what this picture is supposed to indicate. If it includes a point, it includes the whole line. So maybe I can use it as put it as a property 0. This is Zariski closed and yeah. All right. So this is what we can do in general. And now let's look at specifically the set of local systems and see how these definitions apply there. Now, application to log 6. And first of all, I just said that log 6 is a stack, it's not a scheme. Fortunately, we have this one property here that tells us that singular support behaves nicely with respect to smooth pullbacks. So as long as you can cover something in a smooth way, you can test the singular support after pullback, and that works ideally for stacks. So suppose that I have, so now let X be a, let's say, quasi-smooth derived stack or classical degree stack, which or locally complete intersection classical stack whichever one you prefer, quasi-smooth derived stack, then we can define sing of X and singular support of sheaves on X or on its open subsets. So we can define it locally in the smooth topology using this last law. Smooth ice. So somehow once the theory is set up for schemes and it has this property, that immediately extends to stacks. So, and the example where, so I guess this side of the board is for examples. So the example we are particularly interested in is this, the stack of local systems. And so again, I'm skipping a lot of details, but let me at least sketch the calculation. So I want to calculate this string of local system, this shifted potential bundle for local systems. So string of local is me. And so in other words, I have to, in order to understand this, if you like, by definition, this is going to consist of a local system and I denote it by L to sort of avoid choosing between two different points of view, whether it's a vector bundle with a connection or a G bundle on the Durand stack. So, and then I want to have a shifted cotangent vector H minus 1 T star of the stack of local systems. So yeah, so the stack of local systems at this point. Okay, so let's see what's happening. I guess if I look at the tangent space, as a complex, local tangent space to local systems at L, this is going to be controlled by the Durand homology. So the Durand homology of our curve with coefficients with coefficients classically in endomorphisms of this local systems or local system, or you should say like the infinitesimal endomorphisms. So I have a version of the Lie algebra listed by my local system. And so, and there is a shift involved. So the first, the tangent space will be the first Durand cohomology, and the first cohomology of the tangent complex will be abstractions to smoothness, which is controlled by H2. Now, the reason I'm looking at H1 of the tangent space is because H minus 1 of the cotangent space is dual to this. So psi is going to be a linear functional in this space. Which I can compute by duality. So this is by Verdier duality. This is going to be dual to H0 of the same thing, where I use the fact that because G is reductive, I can identify G with its dual. And so what this means is that psi is basically, if you like, an infinitesimal symmetry of my local system L. So in more classical terms, I mean, I start with a local system, then I construct from it a vector bundle using the adjoint representation. This is going to be a local system of vector spaces, or in fact, Lie algebras with fiber G, and psi is a horizontal section of this local system. Okay, and so the reason we care about this calculation is because now I can, the fact is that once I have an element in the Lie algebra, I can ask what its eigenvalues are, or more precisely, I can ask whether it's nilpotent or it fails to be. So I can, in particular, deserves its own place. Let me get rid of this example. So I can now define the subset called the global nilpotent cone sitting where the singular supports of coherent sheaves live. So sitting in here, and I'll define it to be the set of such pairs L psi, where psi is nilpotent, as a section of a local system of Lie algebras.
We have a question.
Yes.
Can you explain the GL?
GL is, so if I have a G torsor, I can twist any representation of G by this torsor and get a vector model. If I have a G local system, I can twist any representation of G by this local system and get a local system of vector spaces. So GL is the twist. So I think in Justin's talk, this would be denoted by G times G. G superscript. Better. Yes. So does it answer the question? So, and yeah, I mean, really, it's enough to understand what happens in the case of GLM. In the case of GLM, this is a local system of endomorphisms of my vector. Okay. All right, and so the point is that this thing, on the one hand, it contains the zero section. On the other hand, it's contained in the entire thing. So this means that I now have an intermediate condition. So if I have a coherent sheaf, I can look at its singular support. If I have a coherent sheaf on local system, I can look at its singular support and ask where it falls, whether it falls within the nilpotent cone. So I know that its support always contained in this. If it happens to be contained in the zero section, that means that my F is perfect, so it's locally has a finite projective resolution. But now we have something intermediate. So if the singular support is here, then it's allowed to be non-perfect, but only in some very mild way. Yes.
Could you just touch again on point one that you just mentioned also?
Yes.
F is bounded for amplitude that its singular support is contained.
Right. Touch on it in the way of like I can prove it basically. Will it? Yeah. Yeah. So so somehow the point is that point one, saying that the singular support is contained in the zero section, is equivalent to saying that the equations of the zero section act nilpotently. So in this language, it's equivalent to saying that this cohomological operator become nilpotent or in the X algebra. And because the X algebra is finitely generated as a module over this cohomological operations, it's going to be nilpotent if and only if this is bound. So these operators are the only things that raise the degree. So if they're nilpotent, that means you can only raise the degree up to a certain point. And then it's well, I don't actually know who to attribute the result to. It's more classical than classical. That F is perfect if and only if this X is bounded. Right. So this is intuitively going back to the definition. When we say about directions of non-vanishing, you can also say that singular support is about measuring the difference between things of finite Tor amplitude and infinite Tor amplitude. And by the way, going back to the case of, let me say this, going back to the case of a hypersurface of a single equation. When you have a hypersurface, this space is going to be one-dimensional, so there are only two things that can happen to the singular support. Either it's zero or the whole thing. And this property 1 tells you completely when this happens. So it's going to be the whole thing if F fails to be finite Tor dimension near this point. Okay, moving on.
You say again what that nil.
So what this condition means? So the point is that, can I just say it in the case of GLN? So in the case of GLN, L is a vector bundle with connection. Psi is a horizontal endomorphism of this vector bundle. And if it's an endomorphism, I can ask whether it's nilpotent. The point is that, by the way, because it's horizontal, if it's a nilpotent at one point, it's going to be nilpotent. It has constant Jordan form, so to say. If it's nilpotent at one point, it's nilpotent everywhere. So it's not like technically you can impose this condition at all points, but it's only one condition. Okay. Now, what second part of the story which is the first part of this title. So what and at least in the beginning this will be very general. So I want to talk about coherent sheaves, and informally this is our way to modify the category, the quasi-coherent category. So int coherent sheaves on a scheme. And here really it's, I'll put derived in parentheses, but because it doesn't really enter the discussion. And so, right, and so the point is that there are two, like the general framework is that there's going to be two different categories of quasi-coherent sheaves. So this is our usual category of what I guess traditionally would be the unbounded derived category of quasi-coherent sheaves on X. And so our goal is to demonstrate or to construct another category, which we call the category of incoherent sheaves on X. It can be, it can be constructed by some categorical, by general categorical ideas. It has also been it also appears in some more, again, I'm tempted to say more classical situations. So, I'm making. I mean, if you're interested, ask me later about other approaches to this. Okay. But purely formally, my goal is to define this category, which generally will be an enlargement of this quasi-core, in order to make this. Well, let me maybe do what Sam did and say that I assume that X is a good derived scheme, which in practice probably means that it's finite type and eventually co-connective. So basically bounded structure sheaf, which is going to be necessary if you want to go with the derived view. Okay, so what happens in this case? So, and it's easiest, the easiest way to explain what happens is to go back to this case, to go back to quasi-core and analyze it categorically as follows. So let me try to draw a big picture. So replace one big picture by another. So and maybe I can even avoid writing on stage. Yes.
Which local systems are linear coherent.
Very few. Right. So, like for example, let's say we work with GL2. Right. So if the local system is irreducible, it's not going to admit. Like I mean, over GL2, okay, there is always a constant automorphism or constant endomorphisms, but those are not important. I don't have to worry about those. So, so irreducible things will not have any other endomorphisms. I don't have to worry about it. So now I have to look at reducible local systems, and if they are rank 2, it's an extension of one dimensional local system by another one-dimensional. If these two one-dimensional local systems are not isomorphic, then I don't have to worry about it. And in fact, I mean, if I want to have a non-nilpotent map, I mean, this non-nilpotent map, well, I guess technically I have to worry about scalar. Let's say I'm talking about SLP. So if you have something non-nilpotent, then it has distinct eigenvectors. And so that means that your local system needs to be a direct sum. So.
No, wait, you can have an interpretation of two isomorphic ones.
I can have an alternative. So, but what is the question? The question is which admit nilpotent or which admit non-nilpotent?
Nilpotent.
Ah, yes, of course. For nilpotent, of course, the interesting case is exactly where you have an extension of one local system by itself.
And is the locus related to the global nilpotent cones in the Higgs bound?
I would say that it is its counterpart where you look at Higgs bundles on the Durham set, right? Where you say local systems instead of.
So I found it not to be in part of it. I guess it's.
I don't think so, but. Okay. So. Right, so the big picture. So first, I have the category of quasi-coherent sheets. Let me say this will be the big side of the board. So for big, there is quasi-coherent sheet of X, and this is when I say a big category, that means it admits arbitrary co-limits, so it's co-complete, admits. And moreover, it's compactly generated. So since Sam technically wrote the definition of compact objects, I'll just say that we can consider from this category, we can take compact objects. So, and consider so these are the compact objects in this category, and the compact objects will be exactly perfect complexes. So coherent sheets, which in particular have which coherent sheaves, which also in addition locally admit finite resolutions. And so the fact that the category is compactly generated means that, in fact, it's not just that this category is determined by the category quasi-core by general categorical nonsense, but it's also true the other way around. I can take, instead of taking the compact objects, I can take the general procedure called incompletion and recover, well, you can say the incompletion of the category Perf will be identified with the category of quasi-coherent sheaves, and where incompletion you can think about it in two ways, in one of the two ways, both of which are very useful. So the incompletion, you either think of it as adding formal co-limits, or limits, or you think about it as kind of representing certain functors from this category, or the set of the category of functors, I guess, contravariant functors from Pure or to that, to the DG category of that. And this general kind of framework, I mean, exists in different setups. You can do this for usual categories. You can here we're doing this for infinity categories or stable infinity categories as it happens. But the general framework, I mean, you have to understand exactly, maybe work a little bit with the definition, but again, the general framework is actually existed for some time. Okay, so we have this, and now, so somehow from this point of view, whenever you work with quasi-coherent sheaves, you secretly rely on some properties of perfect complexes. And the fact is that there are certain constructions that naturally call for coherent sheaves rather than perfect. So besides this perf, we also have the category of coherent. Yeah, I know, I'm going to fix this in a moment. So we also have the category of coherent sheaves, which is large. And and then plugging it into this categorical framework, I can take its incompletion. And that's by definition what incoherent sheaves are. So purely formally, and in fact, I mean this with a convenient ways to think about them, you can either think about them as some kind of extension of coherent sheaves using formal co-limits, or as the category of functors from the opposite of this category to that. So now there are some nice comments about this, but maybe maybe let me finish this idea and then we'll see if there's any time left. So okay, so we have this, and now the point is that we can put the first part and the second part together in the following way. So suppose that we work with this framework, and suppose that our X is actually a local complete intersection. So suppose that it is quasi-C. So then I can think of this perfect, we just discussed that this perfect subcategory within core is basically cut out by a singular support condition. So if X is now X is quasi-smooth, I can add pictures to this category. So I have here for X, I'm going to allow arbitrary singular support. So I have entire sim X. And for perf, I only allow the zero section. But this means that now whenever I have anything, any conical subset, for such as this nilpotent cone, for instance, I can use it to restrict the class of compact generators. I can use it to consider a smaller category, a subcategory within the category core, and then consider only the subcategory generated, consider only the incompletion of this category. So I think of the singular support condition as a way to generate versions somehow, versions of the category quasi-core. So in general, here, for example, I have this global nilpotent cone, which is neither too big nor too small. It's smaller than the whole thing, but larger than the zero section. And so this means that there will be, for a subset like this, I will have a set, the corresponding set of coherent sheaves sitting in between the two, and I will have the incompleted category sitting between the two. So let me try to summarize this question. So now, given a conical, I'll denote it by n, seated in this shifted cotangent bundle in sim of x, we can define the corresponding version of incoherent sheaves on x and to be the incompletion of not of the entire category of coherent sheaves, but only restricted to the coherent sheaves with singular support contained in n. And before so, and something's not quite right on the board, so let me fix this, and then maybe I'll be done. So I want to say that this definition works as written when you work locally, when you're on a ski. If you want to play this game for stacks, we know that you want to localize things, but so you want to consider maps, smooth maps from schemes into your stack. The point is that you have to localize in a particular order, namely, so as a remark, this definition as works as written. Let's say for a fine, let me just say works locally. In general, for if you want to use it for quasi-smooth stacks, the right stacks, define IndCoh of a stack, perhaps. Yes, and let me actually call the quasi-smooth stack X. So if I call it X, then I'm going to define it by considering all basically by gluing the categories for all possible smooth charts. So this is going to be limit of IndCoh S. Let me actually put this for S to X. This is smooth. So where S has to be aligned. So that we're in the previous one. So okay, so we have this kind of general definition, and now we can, in particular, we can apply it to the example, to the situation that we are interested in, specifically to the global nilpotent cone of sim log cis. And so I can now, I think I made sense of one line in Sam's talk, and the line was something along, at some point you might be tempted to write this kind of category, and what you really should write, so this should be replaced with IndCoh log cis g check nil. I think he probably put nil here. That's not even something. So I explained what this category is. In fact, from the construction, you can see that it contains, that it's an enlargement of this category. It has certain nice functorial properties that I don't have time for right now, but I don't know if they will be discussed at a later point. Anyway, so a short summary is that this is, in some way, it's not that different from this. The difference is measured by some, it all goes back to relaxing the condition that certain objects are perfect by keeping track of how cohomological operations act on those objects.
Can I ask a question?
Yes, please.
So what is the reason so for the stack you don't you go through the leading procedure rather than
Right. I mean, the other possibility would be to somehow consider coherent sheaves on the stack, then we consider an important support there, and then take the incompletion. So that will correspond roughly speaking to permuting these two constructions. You take the limit of coherent sheaves, this will be the same as a coherent sheaf on a stack, and then take incompletion. So roughly speaking, in order for this, so sometimes this is correct. In fact, for log cis, this is correct. But it's correct for a non-trivial reason. It's basically, in order for this to work, you need to know that this category is compactly general. So, for example, I mean, if I try to play this game for arbitrary stack, we don't know that the category of quasi-coherent sheaves on an arbitrary stack is compactly generated by curve. Oh, it's compactly, if it's compactly generated, it's compactly anyway. So we know this locally. And so if we want the universal answer, if we want the robust answer, then the easiest way is to do it in this order. So this order is always correct. The other one is a field, which sometimes holds and sometimes doesn't.
Let's declare a break, and then the speed can be interrogated on the blackboard as no.
Yes.